Okay, good morning. Let's jump right away into example 1 for AC power. So, did anyone review the examples? I've not yet had a student in either of the sections in the morning say yes. Okay, that's better than nothing. Okay, any questions on the approach we have taken thus far? Any questions? All right. Okay. All right. So we stopped right here. We found ZEQ as seen by the source. We applied Ohm's law, and then we found I, total current I flowing through the system, right? The question being asked here was find the power for all components, including the source. So we can take two approaches. The first approach is basically find all the individual powers, R, L, and C, and then you add it all up. Law of conservation of energy states all of the power delivered by the source is absorbed by the components, by the loads. So if we find or determine all the individual powers and add it up, that would give us the total power delivered by the source. Make sense? So that is the approach. That is the approach for the first half. Now, when you have the current, you can use these equations. V equals IR and P equals VI. If you wish to find power, you need either the voltage and current, right? If you have voltage and current for any component, you can find power using this expression. Or if it is a component like a resistor or inductor or capacitor, you can use any of these four equations. So if you use any of these four equations for the component, you again need either voltage or current, and you need the resistance or the reactance. P is V squared over R or I squared times R. Same equation for reactance X. So if you have total current I, we can find the power for the inductor. IL times XL, or sorry, IL squared times XL. Same structure of the equation. If you have voltage across the inductor, you can find it as V squared, VL squared divided by XL. Make sense? And I will show you both. I have both. Okay. If you have I, that I flows through both the inductor as well as the parallel combination of the resistor and the capacitor. So if you apply Ohm's law, you can find voltage across the inductor and you can find voltage across the capacitor and resistor ZRC, which is this equation right here. Okay. VR is the same as VC. You can obtain by Ohm's law, IZ, I times ZRC. Same principle, you can find the voltage for VL, I times ZL. Okay, I times ZL. Make sense? Yes.
If you're using the VR and the VC would have
It as usual. The question being asked is how would we use it for a resistor as any complex quantity? For a resistor, you can have an angle. The difference between a resistor and inductor and capacitor is that the current for a resistor will have the exact same angle, meaning the difference between the two is 0. So the voltage and current for a resistor is a complex quantity. and can have a non-zero angle. But the difference between the two phase angles of voltage and current for a resistor would be 0. So if we find the voltage for the resistor, we find it minus 180. And we're jumping ahead to the final value. So let me bring this up. Here, I have applied, what have I applied? Voltage division. You have two impedances in series, voltage being applied to two impedances in series, like voltage division, and you can find voltage that way. So again, two different approaches to finding the voltage. One using Ohm's law, the other one voltage division. The answer you obtain should be the same one that I have, 10 with an angle of minus 180 degrees. And we treat it as any other complex quantity. When you find the voltage for, when you find the current for the resistor, it has the exact same angle, no difference. Right? No difference. Because the resistor itself doesn't have any angle. So when you take V over R, it's the same angle minus 0. And so voltage and current would have the exact same angle. It does not affect, it's not an energy storage device, so it does not delay the current or the voltage. So they're always in phase. Voltage changes, then current changes at the same time. So again, practice these calculations. As a reminder, big quiz coming up on Monday, AC analysis plus AC power. It's about 35, 40 minutes long. And I won't be testing those topics again in the final exam. So show me your best work. Okay. You have plenty of time to prepare for that quiz. So now I have voltage and I have current. I have voltage and I have current for for the capacitor and for the resistor. I can use either the voltage equations or the current equations to find power. So on the left here, I have used voltages. And I have left one quantity for you to practice. That is the inductor. On the left is voltages, on the right is using the currents. This is just to illustrate the point that no matter which approach you take, your answer should match up. 0.5 watts, 0.5 watts, minus 0.5 VAR, minus 0.5 VAR. Here, of course, I haven't done it, but I will assign as practice for students 1 VAR and 1 VAR. Okay, the answers should match up. Now, as students, when you're giving an exam or a quiz, you would not always have time to solve the same problem with multiple different approaches. But as engineers, as working and practicing engineers, it would be expected of you to verify your solutions in real life. Because no company is going to put companies do put products out there without testing it completely. But I wanted to say, as an engineer, you would not want your solution to be out there or released to the public without verifying it, right? So as engineers, as working engineers, if you come up with a solution to a problem, you will be required to verify it with multiple different ways. That's what you need to do. You need to verify your answers using multiple different approaches. And so that's what I'm showing you here. Now, what you choose is up to you as an engineer. Yes. It does matter. Yep. So the question being asked is, does the phase angle matter or not for the power? The answer is, it does matter. Yes. These are complex numbers, complex quantities, so phase angle always matters. So depends on the equation. So if you're taking just the equation for VC or X, then it's just RMS value divided by the reactance. Okay, so that's just the RMS values. Then it's just the magnitude, then this would not be any angle. Yes. Mm-hmm. No, that's the same current I. So the question being asked is about the currents that are coming. Because it's a series circuit, the same current I is flowing through all three components. Now the capacitor current and the capacitor and the resistor current are different, IR and IC. And so those we have determined here. Those are different. The magnitudes turn out to be the same because the resistor magnitude is 100 ohms and the impedance for the capacitor is also 100 ohms. The phase angles are different. And so once you have individual components, all you have to do is add them all up together and you have your total complex power delivered by the source, S, in the entire system. Okay. Remember, QL is always positive, QC is always negative. Eli the Iceman, voltage always leads the inductor by 90 degrees. So QL is always plus 90, QC is always minus 90. Okay, so you always put a minus in the equation for QC. So when we sum up the total reactive power in the system, QLs, all the inductors will have positive Q, all the capacitors would have negative Q. In real life, obviously, there is no positive or negative. It's simply the mathematical notations, right? So plus 1 and minus 0.5 gives you a total of 0.5 plus J 0.5. Make sense? Let's take a pause. Let me know if you have questions. Yes. XL and XC. XL is the reactance for the inductor. It's 1 over 2 pi F. XL is 2 pi FL. XC is 1 over 2 pi FC. Chapter 5. And then ZL and ZC is, of course, J. And then ZC is minus J. Minus J over 2 pi FC. Right, any other questions? Do the steps make sense? Yes. Sure. Here. How far up? Okay. So again, the purpose of this problem is, of course, it's a 2-in-1 problem. First half is AC analysis, where we determine the voltage and the currents associated with each component. And then we use those voltages and currents to determine the power for each component. So that would be on the quiz on Monday. Okay. So a second approach would be to find the total source power. And total source power can be determined from these equations. This is the first set of equations that we looked at. These equations can be applied to resistors, inductors, capacitors, or any source. Okay, you can apply this to any component you want. But whichever component you apply it to, you need the voltage and you need the current. You need V and I, right? If it's a resistor, resistor only has real power or average power P. It does not have any Q. So use only the first equation. Inductors and capacitors do not have any average power or real power, so they do not have P. You only use the equation Q. A source will have both, depending on the circuit, of course. So you need, well, not need, but you can find total power by using both equations. And both equations have three quantities: voltage, current, and the power angle theta. Power angle theta is the phase difference between the voltage and current angles. So in reality, you only need the values for two quantities, voltage and current. So if you are trying to find the source power, then you need the source voltage and you need the source current. Source voltage is given to us, and source current is something we calculated, which is right here. So we have the magnitude, we have the phase angles, we calculate the power angle for the source, theta V minus theta I gives us 45 degrees. That's the power angle for the source, 45 degrees. Then from that point on, it's a simple plug in. You take the standard expression, plug in the known values, right? It's RMS values. RMS values are magnitude divided by √2. So you have 10 divided by √2, and you have 0.1414 divided by √2. Both of the magnitudes of the voltage and current. You obtain the exact same values, 0.5 watts and 0.5 VAR. So this is kind of like the top-down approach. Same answer, no difference. Okay. And I say it's the top-down because you're trying to find the total power for the entire system being supplied by the source. It does not give you the individual powers. There's only one resistor in the circuit, so yes, we can state 0.5 belongs to the resistor. But there are two reactive components. So total Q in the system is 0.5, but we don't know what the inductor QL and QC is. We still have to do further calculations. So again, your approach should match up with what is required or what is asked of you, right? And this is just to illustrate a different pathway. So what do these mean? If you were to draw the power triangle, E is on the x-axis and Q is on the y-axis. You join those two together, you have magnitude of S. So power triangle, real power P on the x-axis, reactive power Q on the y-axis. Total reactive power is QL minus QC, which in this case is 0.5 VAR and P is 0.5 watts. You join the two together, the hypotenuse of the right angle triangle, you get the magnitude of S. QL required is 1 VAR. QC required is only 0.5 VAR. So it brings down the total required reactive power from the source from 1 VAR down to 0.5. So this is without the capacitor. This is with the capacitor. Remember, when the switch is flipped, the source is required to send 1 VAR to the inductor. Inductor absorbs the power, sends it back, and the capacitor size is such that it can only absorb half of that. So it's 0.5 is absorbed. And from that point on, the capacitor supplies 0.5 VAR. And the source is now only required to send 0.5. Okay, so the power required from the source is now reduced. So capacitor is now supplying half of that required power. So it reduces. Capacitor reduces total Q required from the source. designing a system and choosing the value of value of C is known as power factor correction, which for those of you who are taking the lab is lab 8 for this week. How many of you are done with lab 8, by the way? Wow. Does it make more sense now? Hopefully. It's just unfortunate the way holidays come up. For those of you who are taking the lab this week, this is what you're doing in lab 8. You're using a value of capacitor to balance out the requirements from the inductor. Okay, power factor correction. Obviously, the capacitor size is large enough. It can absorb 1 VAR and then supply 1 VAR from that point on. So the source would not be required to send, any reactive power. But that's an ideal system. It never happens that way in real life. Okay. All right, questions? Any questions? Do both approaches make sense? Yes. There's a third approach. We can use another equation, which is S equals half VI asterisk. This is only for current. We have the voltage for the source. We have the current for the source. We can apply, well, again, you can apply this equation to any component. These are phasors, voltage phasor and the current phasor. For the I asterisk, the asterisk notes that it's the complex conjugate of the current. Complex conjugate simply flips the quantity around the real axis. Plus becomes minus, minus becomes plus. You have the voltage, you have the current. Plug in the values into this equation, and you obtain the exact same answer. 0.5 plus J 0.5. One-step answer. Third approach. This is the third approach to finding the total power. But again, in all cases, you need either the voltage or the current, right? The source does not have any resistance or reactance, so you can't use the V square over R or I square times R equations. But for all components, you can use all three sets of equations. In the quiz or in any exam, it's open book, open notes. You can have all of these equations open and have all the notes open. Show me your best work. All right, let's take a pause. Let me know questions. Let me know if you have any questions. Yes. Yep, that's it. Question being asked is about power factor. Power factor is basically the cosine of the power angle. And it's important. So it's an important question. So if you look here, the angle is much larger. And this is smaller with a capacitor. So when you have a power factor, this is used in everyday life. Power factor indicates how big or small that angle is. The highest power factor is 100% or 1. 1 is cosine 0. If the angle is 0, means if my QL was required this much and my QC supplied is exactly equal, then my angle is 0. Cos of 0 is 1. So 100% is the highest power factor. All other values are less than 1. Okay. So the higher the power factor, the lower my angle. The lower my angle, the better my system. So power factor is used to describe the requirements of the reactive power, which we want the power factor to be as high as possible. Which brings us to example number 2. It's a very interesting problem. I really like it because not a lot of information is given outright. There's a lot of inferences and deductions and conclusions that we have to make from the presented information. Okay. Circuit diagram is not given. This is simply a system diagram. And what is given is there are two loads, A and B, and there is one source. Okay, one source voltage. Value is given for the source voltage. Element A is given, element B is given, or actually it's load A and load B. We are not given anything else except for certain values. And we are asked to find the total complex power for the source, meaning we also need total complex power from all the components. And we are asked to draw the power triangles for all three, for the load as well as the source. So this is how you would use power triangles to analyze a system. Okay. So as engineers, and I repeat this phrase all the time, it's as engineers, you should be detail oriented. You should look at the problem statement and extract as much information as you can. In here, the information is kind of buried in the units and also in the words leading and lagging. Even the values 0.5 and 0.7 have some meaning, and I will explain each and every one. Okay. Let's take element A first. Well, let's take the values 0.5 and 0.7. Okay, 0.5 and 0.7. Just a few minutes ago, I stated, what is our highest power factor? 1, right? 1. If power factor is 1, what does it mean? 100%, and my angle is 0. Reactive power is completely 0. The only power in the system is the real or average power P. So if it is not 1, what does it mean? It means there is real power and there is some reactive power in the system. Think on it for 10 seconds. If the power factor is 1, it means there is no reactive power in the system. For all other values of power factor, there is real power and there is reactive power. So this has P and it has Q. This also has P and it also has Q. So both loads have an angle, which means they have real power and they have reactive power. Does that make sense? Right? That's the first inference. Okay. And now if they have P and they have Q, they also have magnitude of S. That's a third side of the right angle triangle. Right? The power triangles. Yeah, remember, go back to the slide right here. You have P and you have Q. This is the magnitude of S. Apparent power. That's total complex power. And then apparent power, magnitude of S. That's the third side of the power triangle. So if it's 1, that means there's only real power. There's no reactive power in the system. For all other values of power factor, there is real and reactive power in the system. Okay. Next, 0.5 leading. Eli the isomat. Chapter 5 at the beginning. Voltage always leads the current in an inductor by 90 degrees. Hence, inductor impedance is plus 90. Hence, the reactive power for inductor is also plus 90. Whereas for a capacitor, the current always lags by 90 degrees. Hence, the impedance for a capacitor is minus 90. And the reactive power for a capacitor is also minus 90. Plus 90, minus 90. Right? Power factor, the reference is the voltage and we state the position of the current with reference to the voltage. If current lags the voltage, power factor is lagging. If current leads the voltage, power factor is leading. Eli the Iceman again. For an inductor, the current always lags or is behind the voltage. Current always lags the voltage in an inductor, hence power factor is lagging in an inductor. When it says leading, current is always leading in a capacitor, hence power factor is always leading. So when it's leading power factor, it always refers to a capacitor. When power factor is lagging, it always refers to an inductor. Okay, so if it's leading, it's a capacitive load. If it's lagging, then it's an inductive load. That's the second inference. Okay. Element A has a overall capacitive load. Element B is overall inductive. Now, power triangles have four quantities: the real power or average power P, reactive power Q, the third side of the triangle, magnitude of S, and the power angle theta. To find any of the two quantities, you need at least two of those quantities. Make sense? Right? You need at least two quantities to find the third and the fourth. So we have the angle from both. 0.5 and 0.7 is given to us. In both cases, cosine of theta is given to us. We can find the power angle from the power factor. Make sense? We can find the angle theta from the values 0.5 and 0.7 because that is the cosine of the power angle. Cos theta is 0.5, cos theta is 0.7. So we can find the power angle for both A and for B. Now, if we have the angle, there are three sides of the right angle triangle. We need at least one side. And then we can use any trigonometric identity to manipulate those equations. Make sense? This is where the units come into the picture. Let's take watts first. 5,000 watts. K stands for unit prefix kilo, 10⁻3. So 5 kilowatts, 5,000 watts. If it's watts, what does it indicate? Real power P or average power P. That's indicating P. So I have PA. I have theta and I have P. I can use those two quantities to determine QA and magnitude of SA. A, of course, is a subscript for element A. And then this, of course, is for B. So, kilowatts is for B, not for A. So 5 kilowatts is associated with B. So PB is given to us. PB is given to us. And we found theta B from cosine of theta. And then we can calculate QB and SB, or magnitude of SB. Now for element A, the power is given as VA. I've already noted on there, but if it's VA, what is it indicating? Volt amperes. Volt amperes is associated with not P, not Q, but with S. And because we're talking about a power triangle, it's the magnitude of S, as you were saying. That's absolutely correct. So kVA, 10,000 volt ampere. 10,000 volt amperes refers to the magnitude of S. So you have the hypotenuse and the angle for element A. And we can find PA and QA from those values. Take 10 seconds, take more time. Let me know if you have any questions. Yes. So, Eli the Iceman, voltage is always ahead of current in an inductor, meaning voltage is plus 90 with respect to with respect to current. So current is minus 90, is lagging. Right? The other way of saying this same statement is voltage leads current, or I lags voltage for an inductor. And for a capacitor, it's the exact opposite. Voltage lags current, or we can state current leads voltage. This is also the reason why the impedance of an inductor and capacitor plus 90 and minus 90. Impedance Z is V over I, which means theta Z is theta V minus theta I. Power factor is the opposite in some ways, because we are stating the reference as the voltage. So if the current is lagging, we say power factor is lagging. If the current is leading, we say power factor is leading. But it comes from the same principle, that the voltage and current have a phase difference of 90 degrees. Okay. Any other questions? All right. So then let's look at how we can determine the values. Now we have set up the problem and we have two quantities. We can use any trigonometric identities to actually determine the other two quantities. So the first one, load A, we have the power factor 0.5 cosine of theta. We find theta as 60 degrees. Once you have theta, you can simply plug it into the equations. P is VRMS IRMS times cosine theta, and Q is VRMS IRMS sine theta. P actually is very straightforward because magnitude of S is V times I, VRMS times IRMS. So magnitude of S is given to us and power factor cosine of theta is given to us. All you have to do is multiply it. That gives us PA. 10,000 times 0.5. And then QA is sine theta. Find QA, you find the total power, total complex power for PA. Sorry, element A, load A. And of course, power factor is leading. So if it's leading, it's a capacitive load. Capacitive load means you have a minus sign next to it, minus 90. Same thing for element B. Element B, we have power factor 0.7. So we find cosine of theta is 0.7. So theta is 45.57. Now, we have the angle, we have power P, real power P for load B. Angle and power. It's a trigonometric identity to choose to find the third side. Tan theta is Q over P. Depending on the quantities you have, you can use any equation you want. As we have seen, you can take multiple equations and multiple approaches to finding the same answer. Okay, right angle triangle, you have one side and you have the phase angle. You can find the third side tan theta, cosine theta, sine theta. Depends on what values you have available to you. So you choose your approach that way, or you choose your approach accordingly. Make sense? So we have P, we have theta. I use tan theta. Q over P, find Q. And once I have Q, I can find magnitude of S, hypotenuse of a right angle triangle, square root of P square plus Q square. Let's take 10 seconds. Digest all of that. Let me know if you have any questions. Yes. Sure. So the first set of equations, P is VRMS IRMS times cosine theta, and Q is VRMS IRMS times sine theta. And then magnitude of S is VRMS IRMS. So P is basically magnitude of S times cosine of theta, and Q is magnitude of S times sine theta. Remember, magnitude of S is the hypotenuse. And so if you plug in these values in this equation, not values. Next one. Right here in these right angle triangles, if you plug in those values, those are the standard trigonometric equations. Yes.
As far as what question started with, it gave you the Q value.
Let's see. No, it gave us the P. It gave us the P and the magnitude of S. If it was VAR, so the question being asked is how did we know what quantities are given? We determine that from the units. So if it was VAR, then it would be Q. It's a good question, right? VA, so it means it's S, magnitude of S. Watts, W means it's P. If it was VAR, it would have been Q. But again, no matter what quantity is given to you, you have the angle. You only need either P or Q or S. You have two quantities. You can find the third and the fourth. So we found S and P. And then total power, of course, is simply adding it all up. Add up all the average powers present in the circuit, add up all the reactive power present in the circuit. In this case, you have two P's and two Q's, add it all up together. But you have to be careful. Capacitive load means it's subtracted minus. Inductive load means it's added up. And in this case, it turns out that your total reactive power has a negative value, meaning your power angle is now negative. Remember, counterclockwise is positive, clockwise is negative. If it's inductor, positive, capacitor, negative. So if your total required power from the source is negative, meaning overall the system is capacitive. So your capacitor is not only supplying energy to the inductor, but it actually needs more energy from the source. So the situation has flipped. Okay. The inductor and the capacitor are balancing each other out to a certain extent, but then the capacitor is going on. But the capacitor is requiring more power to come from the source instead of the inductor. So inductor supplies power to the capacitor, and the capacitor requires more power, which is the case with the negative angle. Remember, we want that angle to be as close to 0 as possible. But a little bit more up or down means either the inductor or the capacitor requires more energy from the source, which happens. You know, you could design a system based on a certain inductive load. But let's say on a certain day, your inductive load drops way down. Then you have to make adjustments to your capacitive load. Otherwise, your capacitor now requires a lot more energy from the source. So companies have to do that, right? Some days if the factory is down or, workshop is down or something, or the, machines are not being run 24/7, perhaps the load is less. So at that point, they have to flip a few switches, depending on the configuration, and disconnect some capacitors from the circuit. Otherwise, now the capacitors are going to require more energy. Make sense? So then, based on the values of P, Q, and S, you can draw the power triangle for the source. Remember, right-angle triangles are trigonometric identities. You don't have to memorize everything. As long as you understand the approach, right? The equations, I get it. There's a ton of equations and it can get confusing. But again, the equations are all from the same principle. They are the sides and the angle of a right-angle triangle. So trigonometric identities. Okay, they are the sides of a right-angle triangle. But you should understand and know how to use and apply these equations. That's the most important thing. Yes.
Having
Mm-hmm. With either ways, we don't know anything about the system. So the question being asked, I think, is is that the load is capacitor and then the inductor is balancing it out? We don't know. That's one way to state it. Yes, we can state it. Yeah, maybe the load is capacitive and the inductor is balancing it out. But typically in real life, most loads are always inductive, and then we use a capacitor bank to balance it out. Any other questions? Okay, we'll end class here today. I'll see you all on Friday. We'll review some things. I'll answer questions and we'll prepare for the quiz, big quiz on Monday. At least 35-40 minutes, I would say. And again, I will not assess those topics again on the final exam. So show me your best work.